During last video, we discussed about the emission spectrum of hydrogen or line spectrum of hydrogen. Now in this video, we are going to discuss de Broglie equation or dual nature of matter. In the year 1924, Louis de Broglie suggested that just like light exhibits wave and particle properties, all the microscopic material particles in motion such as electrons, protons, atoms, ions, molecules, etc., these also shows dual character like particle nature and wave nature. In other words, these microscopic properties in motion possesses both particle and wave properties. So here all the microscopic particles, according to de Broglie equation, all the microscopic particles in motion have a dual character, that is particle and wave character. Now in order to get de Broglie equation, first of all you consider Planck's equation. According to Planck's quantum theory, for light E is equal to h nu, where E is energy, h is Planck's constant and nu is a frequency. According to Einstein's equation, you know that E is equal to mc square, where m is mass and c is velocity of light. Now by combining both the equations, that is equation number 1 and equation number 2, we get h nu is equal to mc square. But we know that frequency, it is the ratio of velocity of light to that of wavelength. So nu is equal to c upon lambda. So substitute this value of nu by this c upon lambda, then we get hc upon lambda, that is equal to mc square. By rearranging these terms, we get h upon lambda, this is equal to m into c, or actually not these two terms are exchanged, only this c is cancelled. So here hc and here c square is there, so one of the c is cancelled from here and we get h lambda, that is equal to m into c, or just by exchanging these two we get h upon mc, that is equal to lambda, So in order to apply this equation for material particle, velocity of light c, this c is replaced by velocity of particle v. Actually this equation, it is applicable to the light or photons. So in order to apply this equation for material particle, velocity of light c, it is replaced by velocity of particle v, and then we get h upon mv, that is equal to lambda, where lambda is a wavelength, h is Planck's constant, v is velocity of particle and m is mass. Now but the product of mass and volume, it is nothing but momentum, that is p, and therefore h upon p, that is equal to lambda. So p is a momentum, that is product of mass and volume, whereas lambda, it is a wavelength. Now this equation, de Broglie equation, implies that wavelength of particle in motion, it is inversely proportional to the momentum. Wavelength is inversely proportional to the momentum, and this is the de Broglie equation, h upon p, that is equal to lambda, or wavelength is inversely proportional to momentum. This is for microscopic particle in motion. De Broglie equation is applicable to microscopic particle in motion, and microscopic particles, I told you already, electron, proton, atom, molecules, etc. So this is about the de Broglie equation. Now next is Heisenberg uncertainty principle. In the year 1927, Werner Heisenberg pointed out that we can never measure accurately both the position and velocity or momentum of the microscopic particle at a given instant. Therefore, according to Heisenberg uncertainty principle, it is not possible to determine simultaneously the position and momentum of moving microscopic particle with absolute accuracy or certainty. So mathematically, uncertainty principle may be stated as the product of uncertainty in position and uncertainty in momentum is always equal to some constant, and that constant is h upon 4 pi. So Heisenberg uncertainty equation is delta x into delta p equal to or greater than h upon 4 pi. H upon 4 pi, this is a constant. Now what is delta x? It is the uncertainty in position, and delta p, it is uncertainty in momentum. So product of uncertainty in position and uncertainty in momentum, it is equal to or greater than h upon 4 pi. This is Heisenberg uncertainty principle. Now this equation again implies that when uncertainty in position is small, that is when the value of delta x is small, meaning of this is the position of particle is measured accurately. In that case, uncertainty in momentum will be very high. The meaning of this is there will be error in the measurement of the accurate momentum, or there is a large uncertainty in the momentum. On the other hand, when delta p is small, this uncertainty in momentum is small, meaning of this is the momentum, it will be measured somehow accurately or with less error. At the same time, at a given moment, there will be high uncertainty in a position, that is position will not be measured with accuracy. Actually, product of these two, it should be constant. It is constant, that is h upon 4 pi, and in order to keep this constant, when delta p is less, delta x will be larger and vice versa. So this is what is the Heisenberg uncertainty in position, and as I already told you, the more accurately you know the position, the less accurately you know the momentum, and vice versa. So this is what is Heisenberg uncertainty principle. So after discussion of the Broglie equation and Heisenberg uncertainty principle, we solve some numericals on this concept, and first example is calculate the momentum of a particle which has a de Broglie wavelength of 0.1 nanometer. Value of Planck's constant is given 6.63 into 10 raised to minus 34 kilogram meter square per second. Now this example is based on de Broglie equation, and de Broglie equation is lambda is equal to h upon mv. mv, it is the momentum, or when we rearrange this, we get mv, that is momentum, it is equal to h upon lambda. Now what is given? So Planck's constant is known, 6.63 into 10 raised to minus 34 kilogram meter square per second. Lambda is given, that is wavelength is given, it is 0.1 nanometer. Actually, this constant, Planck's constant, here in unit it's a meter square, and lambda is given in nanometer. So convert this nanometer to meter. So 1 nanometer is equal to 10 raised to minus 9 meter. So lambda is equal to 0.1 into 10 raised to minus 9 meter, that is 1 into 10 raised to minus 10 meter. Now just use the equation, this equation. So mv, that is the momentum, it is equal to h upon lambda, value of h, this is the value of h and this is the value of lambda. When you solve this, it comes 6.63 into 10 raised to minus 24 kilogram meter per second. This is the momentum. Another example, calculate the uncertainty in the position of an electron if the uncertainty in its velocity is 5.7 into 10 raised to 5 meter per second. Value of Planck's constant is given and mass of electron is also given, 9.1 into 10 raised to minus 31 kilogram. So this equation is based on Heisenberg uncertainty principle, and this is the equation: delta x into delta p greater than or equal to h upon 4 pi. Actually delta x, it is the uncertainty in a position, delta p is uncertainty in momentum, and you know momentum p, this is the product of mass and velocity. So this equation can be written as delta x into m into delta v. Delta v means change in velocity, mass will remain constant, so m into delta v greater than or equal to h upon 4 pi. So, or we can rearrange this equation for delta x, that is uncertainty in position, because uncertainty in position of electron is asked. So it is equal to or greater than h upon 4 pi m delta v. All the values are given. So delta v, it is 5.7 into 10 raised to 5 meter per second. Mass of electron is also given. Value of Planck's constant is also given. It is in joule second. Substitute the values. Delta x is equal to, so when this is the value of h, 4, this is the value of pi, 3.142, this is the value of m, mass of electron, and this is for delta v. After solving, we get 1.012 into 10 raised to minus 10 meter. This is the uncertainty in position. Now next example, calculate de Broglie wavelength of electron. Mass of electron is given, moving at 1% speed of light. Value of h is also given. This is the de Broglie equation. Value of m is given, 9.1 into 10 raised to minus 31. Value of h is given. V is 1% speed of light. Actually speed of light is 3 into 10 raised to minus 8, and just 1% means just to multiply by 1 and divide 100. So it comes 3 into 10 raised to 6 meter per second. This is the velocity. Okay, so this 3 into 10 raised to 8, this is the velocity of light, and as speed is given 1% speed of light it is mentioned, so multiply by 1 and divide 100. So the velocity will be 3 into 10 raised to 6, and therefore lambda is equal to, apply this equation now, lambda is equal to h upon mv. This is h, this is mass, and this is the velocity, and the answer will be 2.43 into 10 raised to minus 10 meters. This is the lambda, that is wavelength. So in this way, de Broglie equation and Heisenberg uncertainty principle, these concepts are very simple. According to de Broglie equation, wavelength and momentum, they are inversely proportional. It is applicable to microscopic particle in motion, and according to Heisenberg principle, not possible to measure momentum and position accurately.